So let me introduce the speaker of today. He's Joaquin García de la Cruz. He's from the south of Spain, but he's doing his PhD in Liverpool in the John Moores University. And he's in a very interesting PhD program that combines research in the university and some work at a private company. And he's been working for how many? 6 months, I think. 6 months in the okay, so my son appeared unexpectedly. I'm sorry. Let me put the camera again. Yeah, so he's been for 6 months, right, working in eDreams here in Barcelona. So it was a very interesting coincidence because then he could join us for some journal club and some meetings of the Gaia group. And he's working on a topic with direct relation with what we do, but from the simulations point of view. So he's gonna present on the flaring of the disk galaxies, especially the relation with the merger history of the galaxies in cosmological simulations. So now all yours. I switch off the camera and and share the screen. The talk is supposed to last for like 30 minutes more or less, and then we'll have a discussion later. So all yours.
Okay, thank you very much. I'm gonna share my screen now. Okay, and hopefully you can see it.
Yes, it's working. Perfect.
All right. So thank you, Teresa, and thank you as well for giving me the opportunity to present my work, and thank you everyone for attending. So yes, as Teresa said, my PhD project is about using simulations to study the flaring in thick disks of galaxies. And I'm about to publish my first paper. And so I'm gonna present some of the main results of this paper here. And this project has been done in collaboration with Marie Martic, who is my PhD advisor, Ivan Minchev, and Phil James, who is my second PhD advisor. So the outline of the talk, first, I'm gonna give an introduction on thick disks of galaxies, and then I'm gonna speak about a few properties of thick disks. So I'm gonna speak about whether they are flat or they flare. Then I'm gonna speak a little bit about whether the distinction between thin and thick disk is meaningful or not. Then I'm gonna speak about age gradients in thick disks. And finally, because we use simulations, I'm gonna speak about a little bit the merger histories of the galaxies and how this is connected with all the above. So let's go for the introduction. So what are thick disks? They seem to be in almost all these galaxies. And if you analyze the vertical light profile in the disk, normally you can decompose this profile into two components, the thin and the thick disk. And the thick disk normally is the fainter and more vertically extended component of the disk. And for this decomposition, people usually use an exponential or a hyperbolic second function. And the coefficient that goes inside this function is what we call the scale height. So basically, this is a number telling you how extended the component is. But then in the Milky Way, because we have access to more information, the thin and thick disk separation can be based on other quantities as well, like for example, kinematics, chemistry, or age. But for this talk from now on, when I speak about the thick disk, I'm going to be referring to the equivalent of the vertical light profile in external galaxies, which is the geometrical thick disk or the stellar mass or stellar density criteria. Okay, so what do we know about thick disk? Let's talk first about the shape. Surveys of large samples of galaxies concluded that most thick disks are flat. So this means that the scale height doesn't change with radius. However, more recent studies have found galaxies that show evidence of strong flaring. So if you take, for example, this massive galaxy analyzed by Kasparova et al. In 2020, you see that the scale height increases with radius, right? This is what we call flaring, or a flared thick disk. Then also, this is another example of Mosenkov et al. By 2020, where they link some isophoto shapes with flaring in the thick disk. And then in the Milky Way, the existence of the thick disk flaring and in the outskirts and its amplitude is still a matter of debate. If we talk about the age structure of thick disks, there was this picture of thick disks being red, all, and metal poor components, but there is another picture emerging where more recent work suggests that thick disks are actually very diverse and have complex age structures. So here are a couple of examples. These three galaxies analyzed by Kasparova et al. In 2016. If you look at the green points, which are indicating the age of the thick disk, the shape varies a lot from galaxy to galaxy, and also they're not always very old. If, for example, these are other two galaxies from the Fornax cluster, analyzed by Pina et al. In 2019 using induce. And even though these galaxies seem to have an old thick disk, they also reveal that there are different stellar populations coexisting together in the thick disk. And then in the Milky Way, we know that the thick disks have complex age structures, right? So we know that, for example, around the solar neighborhood, as you go high above the galactic plane, stars get older. But then as you go out in the galactic, in galactocentric radius, stars get younger, right? So the thick disk of the Milky Way is not old everywhere. And actually this configuration is what makes age radial gradients, which were found first by Martí et al. In 2016. Then whether the thing and the thick disk decomposition is physically meaningful, in 2012, Bovi et al. Analyzed a sample of stars around the solar neighborhood, and they divided the stars by the alpha over iron, which correlates with the age of the stars. And then they computed the stellar density of these different populations and plotted it against the vertical scale height. And what they saw is that younger stars seem to have more surface density, but the scale height they are smaller. And as you increase the scale height, as you increase the age of the stars, the surface density decreases and the scale height increases. And when they looked at the histogram, they saw that there was a decreasing continuum and they didn't see any split. So in this case, there was a continuum and there was no actual separation between the thin and the thick disk. But then we don't know if this is the case of the Milky Way only, or in other galaxies, it looks the same or different. And if we go to how thick disks form, many formation processes were proposed. For example, radial migration, or a thick disk form from accreted gas or stars, heating up by a thin disk that is heated up by crossing satellites, or maybe the thick disk was forming a clumpy and turbulent phase at early times. But then there was a conundrum, because lambda CDM would predict that most galaxies would undergo mergers, and mergers were shown to induce flaring in the disk, right? But then most of the observed thick disk were flat, and it was very unlikely that none of these galaxies underwent any merger. or didn't undergo any merger. And so the solution for this contradiction was proposed by Minchev et al. In 2015. And they proposed a mechanism by which you can have flaring mono-age populations, right? But then when they're superposed, you can recover a flat thick disk. So because this is a crucial point of this paper, I'm going to take a little bit of time to explain it in detail. This is a galaxy from the sample of simulations we work with. And you see on the left the face-on and edge-on density maps. And on the right, you see the scale height against radius. And if you look at the scale height of the thick disk with radius, with some fluctuations, but you see that it's mainly flat. But then if you decompose the stars in the disk by age, then more structure seems to appear. For example, if you take the oldest stars, you see that they concentrate mainly in the center of the galaxy, right? And they flare quite a lot as soon as they leave the center of the galaxy. If you go to younger stellar ages, then you see that they spread more through the disk, and they only flare at large radii when they actually don't have a lot of surface density, as you can see in the density map. And this effect goes on and on as you go to younger and younger stellar ages. So basically, the key point is that different stellar populations dominate the surface density of the disk at different radii. And therefore, the scale height of the global thick disk is going to be dominated by those populations. And those populations normally happen to not be flaring when they have a lot of surface density. So that's why you can still have flaring in mono-age populations and recover a flat thick disk. Okay, so let's summarize a little bit what we have so far. Shape, it seems that thick disk might be more diverse than previously thought in terms of the global shape and especially flaring. Also, age structure, a picture is emerging where thick disk can host complex age structures and multiple stellar populations. Then we still don't know whether the thin and thick disk decomposition is physically meaningful or not in other galaxies. And you can have flat thick disk even though if you have flaring mono-age populations. And this flaring we know is induced by merger among other processes. So the goal of this project was the following. For their work in Minchev et al. In 2015, they used 2 galaxies only, one from the simulation, the sample that we work with. So our goal was to explore all the galaxies within the sample and see the diversity that we found in the flaring of mono-age populations and flaring of thick disks. Study the thin thick disk decomposition, to study what kind of age gradients we would find in the thick disk, and finally look a little bit into the merger history and see if we found some connections between everything. So the simulations, they are cosmological zoom-in simulations, as Teresa said. And this is the resolution for the stellar and gas particles, dark matter, and the spatial resolution. And the sample consists on 27 Milky Way-like star-forming spiral galaxies. And these galaxies are very diverse in that they show a large range of Welch fractions, they have different merger histories, and also they have a diversity of asymmetric features like bars, spiral arms, etc. And here are some plots, density and age maps, face on and edge on of some of these galaxies. And you can see how some have bars, some have not, some have strong spiral arms, some not. And then if you look at, for example, the age map in the edge-on plots, you see the flaring of the mono-age populations, but in each galaxy, this flaring happens differently, right? So the population is diverse and we want to study what's going on. So first, let's talk about flat versus flare thick disk. We found mainly 2 cases that for which galaxies have a flat thick disk. One is when basically all the monoid populations are flat. And therefore, there is no agent that could drive thick disk flaring, right? The second is very similar to the one I showed before, where you have flaring monoid populations, but they don't carry a lot of surface density when they flare, so they don't drive thick disk flaring. This plot is very similar to the one I showed before, only that you see two black lines here and here, and these indicate the boundary, the inner and outer boundary of the disk. So here would be the bulge, and this is where the thick disk breaks. So we only focus on the region between these two black lines. Okay, so this is for flat thick disk. Flat thick disk, we find also two cases. One is when you have, again, flaring monoid populations, but in this case, these monoid populations carry enough surface density to induce flaring in the global thick disk, right? Which is the case we're seeing here. And then the other one, oh, sorry, and for this galaxy, you can see that the monoid populations increase their scale height more or less progressively as they increase in age. But then the other case we found was when there is a group of monoage populations that share all the same scale height, right? And they carry a lot of surface density. So they're gonna induce flaring in the global thick disk, but also the scale height of the global thick disk is gonna follow quite closely the scale height of these monoage populations, as you can see here. Okay, so these are some examples of basically the scenarios that we found for flat and flat thick disk. Let's talk about now whether these disks are continuous or bimodal in terms of thin and thick disk. So if you remember this plot that I explained before by Bovy et al. In 2012, we did a very similar plot, only that instead of alpha over iron, we just separated the stellar populations by age. We took a slice around the middle of the disk, right? Like around here, and we did the same plot. So as you can see here, for flat thick disks, the story is very similar compared to the Milky Way. There are no clear gaps, and the surface density decreases smoothly with age and scale height, right? And this is the case for all flat thick disks, actually. But then for flat thick disks, the story is different, because you have a group of stellar populations that have all the same scale height, and that scale height is separated from the rest of the monoage populations. So this translates in two different groups regarding the surface density. So this group of stellar populations live in the thick disk only, whereas this group of stellar populations live in the thick disk only. And therefore, the separation into thin and thick disk is meaningful regarding the stellar populations that inhabit each of these two components. And this is what we call a bimodal structure. And then the other example that I showed before, we couldn't fully classify it into one or another because it is true that the surface density decreases with the scale height, but there are some gaps in the monoage populations, and therefore it's not so smooth. You have some peaks, but they're not really clear gaps. So this is what we call an intermediate case, right? An in-between case. So this is for the 4 examples that I showed before. But let's talk about the full sample of galaxies. So what we did was plotting on the y-axis the average of the scale height gradient for all the monoage populations, and we weighted each one by their mass. And then on the x-axis, we plotted the thick disk scale height gradient, right? So basically, this means flat thick disks, flat thick disks, flat mono-age populations, flat mono-age populations that also carry a lot of surface density with them. And this is what we see. We see that overall, for most of the galaxies, their mono-age populations flare more than the global thick disk. And then if we applied the distinction between a continuous structure or a bimodal structure regarding the thin and the thick disk and the populations that inhabit them, we find that those showing a continuum structure, they tend to be on the left-hand side of the plot, so they flare less. And also the mono-age populations don't flare a lot. And then if we go to those galaxies that show a strong bimodality, they are more flared. The thick disk, the global thick disk is more flared. And the mono-age populations also tend to flare more than their counterparts. Sorry, this is summarizing what I just said. Okay. So now let's jump into the age gradients. So I'm gonna go over the examples that I showed before and explain what's going on. What we did was to take horizontal slices at constant height, and then we computed the median age of the stars and plotted against radius, right? And the height of these horizontal slice is color coded. And this is what we find. We find that we have decreasing radial age gradients, right? And the age increases with height. And this is what you expect, because on the inner part of the disk, older populations dominate the surface density, and in the outskirts, younger populations dominate the surface density, right? And this black dotted line is the age gradient following the scale heights of the global thick disk, which in this case also is a decreasing age gradient because of the same reason that I explained. And a similar case we find also in this other kind of flat thick disk, right? A decreasing age gradient. Then for flat thick disk, the story is a bit different, because the age gradients in the horizontal slices, they're gonna look very similar, also decreasing, because the same effect of different mono-age populations dominating in different parts. But then the scale height only follows a few mono-age populations, right? And so that's why, in this case, for flat thick disks, this age gradient is way flatter than the previous ones. And then this case is also very interesting because we find this sudden drop in age that increases in height as you go further away in radius. And this is the effect of basically transitioning from one group of mono-age populations into the other group of mono-age populations that are also flaring a little bit in the outskirts, right? And so you go from older mono-age populations to younger mono-age populations kind of suddenly because of this gap. And that's why you have this feature here. And the scale height, the age gradient around the scale height of the global thick disk also follows this trend. Okay, so then now after the 4 cases, I'm gonna present the whole sample. So what we plotted here, this is the thick disk scale height gradient, as I showed before. And this is the age gradient along the scale heights of the thick disk. So the black dotted line that I showed before. So again, this means flat thick disks. And then this gray line here means flat age gradients, or basically uniform age. And this is where the galaxies lie. So first, we observe that there is an empty space here. So basically, for flat thick disk, there are no flat thick disk with flat age gradients in their thick disk, right? They all have age gradients. And then if we go to more flare thick disks, they are more scattered all over the place, but most of them seem to group around this flat edge gradient area. So we can also do is apply the same criteria of bimodality or continuum structure in the disk. And finally, we can color code the markers with the mass of the galaxy. And so there's a lot of information in this plot, but we're gonna go bit by bit. First, let's go back again to the flat thick disk galaxies. And as I said, they all show age gradients, and also they all have no bimodality, or they have a continuum structure in the thin thick disk. And they also happen to be very small, they are less massive, right? Then flat thick disk, again, they're more diverse. However, we see that most massive galaxies tend to concentrate towards the flat age gradient area, right? And then what we did also was looking into the merger histories of these galaxies. So I'm going to show the exact same plot, but in this case, the color bar is going to indicate not the mass of the galaxy, but the mass of the most massive merger that the galaxies underwent in the last 9 gigayears. Okay, and so if we look back again at this group, we see that on top of everything that I said before, we can also say that they tend to have quiescent merger histories. And I know that this galaxy looks green, so it underwent a medium mass merger, but I'm going to speak about this one in just a tiny bit. And then on the other hand, most of the galaxies that underwent a massive merger also tend to populate this upper area of the plot, right? So if I go back to this guy, this is Galaxy 106, and Marie Martig and Ivan Minchev have used this galaxy a lot because it's a very good analog of the Milky Way in terms of signatures in radial migration or length of the bar, these dimensions, etc. And we know that this galaxy underwent a medium mass merger, but it was around 8 gigayears ago. So this is also around the time we think Gaia and Enceladus underwent or merged with the Milky Way. But in any case, it was 8 gigayears ago, so it's kind of early times. And this is why we still think that this galaxy has a more or less quiescent major history. So I'm gonna leave the conclusions here. We have flat thick disk galaxies, and they seem to have no bimodal structure, so they show a continuum between the thin and the thick disk, and again, the stellar populations that inhabit them. They tend to be less massive, and they all have age gradients along the thick disk. And also they have quiescent major histories. Then on the other hand, flat thick disk, they're more diverse than flat thick disk, but they tend to have bimodal structures. So the separation between thin and thick disk is meaningful in terms of the stellar populations that inhabit them. And then massive galaxies, or galaxies that underwent a very massive merger, they tend to show no age gradient or very small, right? And so this picture here seems to be in agreement with what we know about the Milky Way so far, whereas this picture here seems also to be in agreement with this more diverse picture of galaxies, especially flat thick disk galaxies, that seems to be appearing thanks to the work of all these people. Muchas gracias. Thank you very much. I'm going to leave the conclusions in the screen, and then I'm very happy to take any question or comment or suggestion that you may have.
Thank you, Joaquin. Thanks a lot. I think it has been a very clear and very nice talk. So time for questions. Anybody? If not, I do have one. We have shown a galaxy that had this, well, several gaps in between the different populations, or several gaps in the surface brightness scale height plot. Does this have a particular relation with the merger history, in the sense that that those gaps also can be related to gaps in the period where the galaxy has not undergone?
Indeed. So Ivan Minchev and Marie Martic looked into this, and they saw that these gaps in mono-age populations, they are induced by mergers. And indeed, also this big gap over here is caused by a big merger. So a merger is behind these these gaps. And in this case, we could say that the merger is kind of the responsible of dividing the thing and the thick disk and the populations inhabiting them.
Could this have a link? Well, it's not 100% clear to me, because this is a very complex matter, but the picture that seems to be emerging from DR2 Gaia data for the case of the Milky Way is that there was a kind of primordial disk that was significantly heated due to this Gaia-Enceladus merger. And after that, another thick disk is formed and a thin disk is formed with an independent story, let's say. Would this picture that you are presenting here match this scenario, like in the sense that there is somehow a truncated history of what we had before the merger, and an independent history after that, creating similar gaps in this space?
Well, I think the first thing that I have to say is that it would be very complex to compare these two. I mean, the galaxy, the 106, is very similar to the Milky Way, but of course it's not exactly the same. One of the things about these simulations is that they don't have chemistry. And so these two disks, right, that you talked about, probably they have different chemical signatures.
Yeah. And
it would be lovely if these simulations would have also chemistry, and we could find some of these cases, some of these tracers, sorry. But I don't know if for the Milky Way, some of these gaps have been found or not. Because, yeah, I guess for the Milky Way, we don't have, I mean, how to say, here I'm analyzing the whole disk of the galaxy. So I cannot tell you how
complicated,
meaningful can be the comparison. Yeah.
Okay.
Because maybe there are mergers, but they don't impact the disk full scale, right? So still don't know.
Indeed. Yeah. Other questions?
Yeah, I have a couple, I guess. Very nice talk, Joaquin. Would it be very easy to use another simulation with chemistry? Because now they're appearing almost on a monthly basis, right? New simulations with almost realistic-looking alpha over iron diagrams to check the of Teresa.
Yeah, indeed. I'm using these simulations that Marie did a few years ago, but of course it would be very interesting using others and see what we find also in terms of chemistry. I think especially it would be interesting, well, everything, right? But especially those galaxies that the the stellar populations living in the thin and the thick disk really are different, and see whether the chemistry also follows that split or not. Yeah, it would be an interesting follow-up.
And I have another question about the masses of those galaxy of the galaxy suite. If I looked correctly, then you had one plot where on the right the masses of the stellar masses of, and they were going up to 10 to the 11.
Yeah.
But isn't the Milky Way like more 10 to the 12? Like?
Yes.
So
Well,
you have to scale them up, right?
Probably. I mean, these are all stellar forming spiral disk galaxies, but they don't mean to resemble the Milky Way 100%. So
yeah.
There are galaxies with different masses within the sample.
Okay, but if I look at this 106, then it's even one of the lighter ones.
Yeah. Yes, we don't claim.
I remember that when this Minchev dial 2013, where they used the G106, they had to like scale everything up, multiply the rotation curve by some factor to make it more, yeah. The Milky Way.
Yeah. So this galaxy.
So the bottom line is maybe they gave you just some old simulations, huh? And
well, but
and
still
evolving very fast, you know. I mean, maybe you can download the. I don't know. It's probably. I know it's a lot of work to do all this. But I wonder how much this is a particular. These are particular results limited to the Martic simulations, or they are generic. They're really.
Hey.
Well, they're just results of baryonic physics in that sense.
Well, I mean, they're all cosmological zoom-in simulations. So it's true that the chemistry part is missing, but then all the other processes, right? And they're still there. So.
Yeah, no, I'm not criticizing.
No, I know.
More questions? Have you looked at the scale lengths of the different populations, or is something that Ivan did no?
No, I haven't looked at them. Basically, after this, yeah, there are so many things that can be done.
Usual, yeah.
Yeah, but yes, no. I haven't looked at them.
I have another question. You're only looking at the last snapshot, or are you analyzing the whole movie of each of the simulation?
For finding the mergers, I go through all the snapshots. But then this is analyzing only the last snapshot. Yeah, so it would be redshift 0.
Okay. And what time resolution does the movie have?
Well, the snapshots are they are only a few mega years apart from each other.
Okay.
Yeah.
So you could study, for example, a migration in
Yes.
almost, in high resolution, temporal resolution.
Yes. I mean, also, for example, another PhD student working with Marie, they needed more time resolution, and they ran the simulations by increasing the number of snapshots to study in more detail a particular process related with the bar. So this is possible, basically.
Okay.
More questions for Joaquin? Okay, then if not, we thank you again. It was a very nice talk. And well, we keep in touch in our meetings. So you're always welcome to join the journal club and things. Even though your days in Barcelona are almost finished.
Yeah.
Good.
No, I will continue joining. And thank you very much for allowing me.
Thanks to you. Thanks for the talk. Okay, thanks everybody for coming.
Yeah, thank you.
Bye.
Bye-bye.